Welcome back to this course. In this part of the lecture, we will look at basics of network architectures and protocols. Some basic protocols will be discussed. So far, we have seen various microcontroller architectures and its programming and some of the driving force for IoT evolution. We also discussed ARM architecture and some of the programming concepts. Today we will look at some evolution of networks, and later we will come back to various new protocols and its standards. When you think about the technology drivers for the Internet of Things, there are three things to keep in mind. First and foremost, the number one is embedded computing. Second, because of advances in MEMS technology and miniaturization, we have a variety of sensors and actuators that are now possible to put into a variety of small devices and put all around the environment and get them connected and build an application. And the third is a wireless communication networking. You should think of wireless communication and wireless networks as the glue that hold Internet of Things systems together, and that is what I am going to talk today. If you look at network technologies for our servers, laptops and desktops and smartphones over the past 40 years, we have developed good understanding of how the design works, how to design them, and how to engineer them, and how you manufacture them. These are fairly standard technologies. Of course, there is a lot of innovations and evolutions in networking for normal computers and mobile devices. But there is pretty good way in which we can predict that evolution and how they are going to evolve into the future. When it comes to network IoT devices and sensors and Internet of Things, this is not completely true. This particular field is much newer, and there is a lot more excitement happening, and there is a lot more innovations in this field. So today, the way in which you go about building an IoT system is to take an IoT device or sensors or build them yourself, then go ahead and build an application, typically on a smartphone, or you might have an application running on a gateway, and then you build a cloud service to process the data once it reaches your service in order to derive the inference from the data that you have collected. And so the focus of today is to or focus of this lecture is to explain you how to think about this networking and what are the key organizing principles and what are the remaining ideas that you will benefit from, whether you are a designer or an engineer or an IoT system developer, whether you are an architect of such system, whether you are managing the engineering or the deployment of a system, so that um, so that what we are going to be taken into consideration of various issues that will be discussed today. Our goal is cover the basics. There are a large number of different approaches, a large number of different standards. Frankly, a lot of confusion which standard to use or which protocols to use if you build a system from the scratch. One of the main messages for today is that one size does not fit all when it comes to IoT networking. Best choice of networking depends on the application. So if you look at the basic definition of internet, an internet means and involves the interconnection of multiple networks into a single large networks. Or when you say internet refers to a success to ARPANET, the Advanced Research Project Agency network. ARPANET was an early packet switched network and first network to implement protocol suite of TCP/IP. Both technologies became the technical foundation of internet. Modern internet is multi-tiered, that include commercial participation, and IP provides a connectionless transfer of packets across the internet. If you look at the applications and layered architectures in 1970s, vendor companies like IBM or DEC, Digital Equipment Corporation, developed proprietary networks with the common feature of grouping communication functions into related and manageable sets called layers. So, we have a layered architecture in all the communication systems. So first it was developed by IBM and the DEC computers. When you talk about the network architecture, it's nothing but a set of protocols that specify how every layer is to function and the defined interfaces between layers. So protocols are the building blocks of a network architecture. Like we have defined, network architecture is nothing but set protocols that specify how every layer is to function and the defined interface between layers. So when it comes to protocols are the building blocks of a network architecture. Each protocol subject, each protocol object has two different interfaces: service interface and operation and peer-to-peer interface. Service interface basically defines operations on this particular protocol, or peer-to-peer interface uh, messages exchange with peers. Like in this picture shows, we have a peer-to-peer interface and a high-level object which interface with the protocol. So what exactly a protocol? So we are when you are talking about protocols, it could be we can ask someone, what is your name? I have a question, or a teacher asks in the class. um, Somebody raises his hand, and then the teacher or the instructor listen to the question and responds. So each and every situation in human to human interface or any real situations, always there is a protocol needs to be followed. Similarly, when we talk about networking protocols, we are communicating with the machines, machine to machine. All communication activity in internet is governed by protocols. So protocols define the format, the order of messages sent and received among network entities, and the actions taken on the message transmission, or the action taken on the message that is transmitted, and the reception. So when you talk about network protocols, we can compare the human communication and machine to machine communication. Someone asks hello and we respond with hello, and what time is it now, we respond with the actual time. In a similar fashion, we can see that a computer or a host raises a query or a request, then the server responds with the answer to the query, and it requests for a particular file or a web page, then the server responds with the requested file, for instance. So network protocols uh, helps in defining clearly the communication process. So the rules which govern the communication. So protocols define the format and order of messages sent and received among the network entities, and the action taken on message transmission and reception. So when it comes to uh, protocols, the OSI, Open System Interconnection, or OSI stands for Open System Interconnect International, or ISO stands for the International Organization for Standardization. So it defines a peer-to-peer interface, how different layers or the whole communication system is divided into different layers, and that the message exchange with a peer. So we say a peer from application to application, or presentation to presentation, or session to session. So in OSI model, we define a 7-layer protocol or 7 layers layered structure. So in application A communicate with application B, the data that is generated from one end to the other end, one peer to the other peer, go through various layers. Here it is important to define a new term, OSA layer encapsulation. Each layer adds its own header. The term encapsulation describes the process of putting headers or sometimes trailers around some data. So in this case, the application A generates some data, and each layer, here we have application layer, presentation layer, session layer, and transport layer, network layer. Each layer adds its own PDU or protocol data unit. By adding a header containing protocol information to the PDU from the layer above, for example, in internet protocol suite, the contents of a page are encapsulated with an HTTP header, and then by an HTTP header followed by a TCP header and a IP header, and finally a frame header and a tailor. The frame is forwarded to the destination node as a stream of bits, and it is decapsulated or de-encapsulated to the respective PDUs and interpreted by each layer at the receiving end. So the data that is generated from application A go through the various layers, and each layer adds its own PDU. Here it is the application header, presentation header, and data. So all data from each layer is encapsulated with a special header, and at the receiving end you can say it is de-encapsulated. So this result of encapsulation is that the lower layer provides a service to the a layer or layer above it, while at the same time each layer communicates with its corresponding layer on the receiving node. These are adjacent layers, interaction or interaction between the layers. So in 7-layer OSI reference model, uh, provides a user access to the OSI environment and distributed information services. If you look at some of the uh, examples, or if you look at the detailed layer standard, the application layer provides access to the OSI environment and distribution services. Some examples could be HTTP, FTP, mail services, etc. Or in the case of presentation layer, provides an application process independence from differences in data representations. So different data representation are there in the computing regime. So therefore this presentation layer provides an application process independence. So the layer should work independent of the of differences in data representations. For example, an image file can come with different formats. So the presentation layer uh, provides a service to to consider different data representation. Also responsible for some of the important service like data compression, encryption, decryption, etc. A session layer provides the control of structure for communicating between applications, establishes and manages and terminates connections between cooperating applications, and maintains sometimes sessions, manages authorization and authentication. For example, SSL is a session layer protocol. So in transport layer, we have basically it provides reliable transparent transfer of data between endpoints and provides end-to-end flow control and error recovery is provided by the transport layer. And the information is divided into different segments, chunks of data plus a header is added on the transport layer. Decides about reliable or unreliable communication. For example, TCP is a reliable communication because every packet is acknowledged, whereas UDP is unreliable because no acknowledgement is given. Unreliable is faster due to less overhead. And also the transport layer decides on port number. We call it uh, IP address plus port number. We define a particular socket. Whereas in the network layer provides independence from data transmission, routing, switching technologies used to connect the system, responsible for establishing and managing and terminating connections. So network layer is responsible for establishing and managing and terminating connections. Segments from transport layer converted into packets. Extra information added as another header. So each layer adds extra information as a header, uniquely identified hosts beyond the subnet, IP addressing or logical addressing. So in data link layer provides a reliable transfer of information across physical layer. So we have when a data goes to physical layer, the data link layer provides a reliable transfer of information across physical layer, sends and receives frames with necessary synchronization and flow control and error control is also provided in the data link layer. Basically, data link layer converts packets into frames and packet plus data link header. The media access control addressing and hardware address for the network card. Basically, hardware address for the network card is called the MAC address, and this also controls the flow control, key flow of data synchronization, and error checking such as CRC and parity is checked at data link layer. Physical layer actually deals with the hardware frames now treated as a sequence of bits in the physical layer. So whatever data that is being passed by upper layers when it reaches to the uh, physical layer, which is concerned with the transmission of unstructured bit stream over a physical medium and deals with mechanical, electrical and functional procedures and characteristics to access the physical medium. So the advantages of layering in the design is that explicit structure of dealing with a complex system. So it provides an explicit structure for dealing with a complex networking system. It's allow identification and structure of relationship of a complex system in pieces. So that is the advantage of layering the system. An explicit structure is defined. It provides an abstraction for functionality and simplify the design process. So the another advantage of layering design is that the modularity of layers eases the maintenance and updating the system's components. Change in implementation of a layer service is transparent to the rest of the system, led to a flexible and modifying and developing a network architecture, and this also accommodates incremental changes. So any particular layer, if we want to make an incremental change, we can do that. The TCP/IP architecture, which an old model doesn't have all the 7 layers like OSI, but it is a 5 layer: the physical network layer, internet protocol, TCP, and application. So TCP/IP or transmission control and internet protocol is a suite of communication protocols used to interconnect network devices on the internet. TCP/IP can also be used for communication protocol in a private network. The entire internet protocol suite, a set of rules and procedures, is commonly referred to as TCP/IP. TCP/IP specifies how data is exchanged over the internet by providing end-to-end communications that identify how it should be broken into packets, similar to OSI model, and how it is addressed, transmitted, and routed and received. Uh, uh, and TCP/IP requires a central management and is designed to make networks reliable, the ability to recover automatically from the failures of any network. So TCP/IP has advantage that if any device fails, it automatically recovers from failures. So main The two main protocols in the internet protocol suite is serve specific function. TCP defines how applications can create channels of communication across a network, and also manages how message is assembled into small packets before they can send transmitted over the internet and reassemble at the destination address. So at the transmission or the source, the data is split into small packets and reassemble at the receiving it. So so here we have five layers which defines the source and destination and the transmission system, and the entire system is divided into five layers of architecture. So if you look at the TCP IP versus OSI, um, now this is the time to compare both reference model that we have learned till now. Let us start with addressing the similarities that both these models have. Following are some of the similarities between OSI reference model and TCP IP model. Both have layered architecture, as you can see. OSI model and TCP IP has layered architecture: application, presentation, session, and transport, network, and data link. Whereas TCP IP has only uh, three, two layers are missing, and total five. So in a way we can say it is four layers. So the layers similar to layers provide similar functionalities. Both are protocol stacks, both are reference models. In OSI, if you look at the differences, OSI is very generic protocol, independent of independence standard, acting as a communication gateway between network and the user, whereas TCP/IP model is based on standard protocols around which internet has been developed. It has a communication protocols which allows connection of hosts over the net. Secondly, the OSI model has a transport layer guarantees the delivery of packets. TCP/IP model, the transport layer does not guarantee delivery of packets. Still, TCP/IP is more reliable. Also, another difference is that flow is vertical. It's a kind of vertical approach. Flows are more horizontal approach. OSI model has a separate presentation layer and session layer, where TCP/IP does not have a separate presentation and session layer. Transport layer is connection oriented. A transport layer can be connection oriented and connectionless. In TCP/IP, the transport layer can be connection oriented and connectionless. Network layer is both connection oriented and connectionless, whereas network layer is connection oriented. Network layer is connectionless. OSI reference model around which networks are built, generally it acts as a guidance tool, whereas a TPS model is in a way implementation of the OSI model. Network layer of OSI provides both connection oriented and connectionless service. Network layer in OSI provides connectionless service. OSI model has a problem of fitting protocols into the model, whereas TCP model does not fit any protocol. The protocols are hidden in the OSI model and are easily replaced with the technology changes. In TCP/IP, replacing protocol is not easy. OSI model defines services, interfaces, protocols very clearly and makes clear distinction between them. It is a protocol independent. In TCP/IP, the services and interface protocols are not clearly separated. it also a protocol independent. It's also protocol independent. There's 7 layers, and in TCP we have 4 layers. So the so if you look at the internet protocol stack, we can ignore, or we can typically we talk about 5 layers: application, transport, network, and a link layer and physical layer. Application support, for example, FTP, SMTP, and HTTP. Whereas in transport layer we are talking about TCP and UDP. Network layer we are talking about ICMP or IGMP or IP networks. They are dealing with transfers between neighboring elements like PPP or Ethernet are the typical. So in the layering example, a client server relationship is defined. The server process waits for incoming requests by listening to a port. Then client process makes a request as required, and server process provides a response to the request. So server process usually runs in the background as a daemon. So if you look at the HTTP example, a hypertext transfer protocol specifies rules by which client and server interacts to retrieve a document. So specify the rules by which the client and server interacts. The protocol consumes the client and the server can exchange messages directly. The protocol assumes that the client and the server can exchange messages directly. The client software needs to set up a two-way connection prior to the HTTP request. So an HTTP request is sent from the client to the server, and the server responds. So that is usually a series of communication happens between the client and the server in getting the required web page or service. So like I said, if client server interaction happens, each layer or the HTTP request header contains this source and destination. Each TCP IP protocol stack adds TCP header and IP header, and the link layer, the Ethernet header, and the final frame sequences added. So if you look at the uh, animated encapsulation of transmission, each at the source, let us assume that the message is generated, and transport layer, a segment is added or header is added, and the network network layer, another header is added. So and in the link layer we make it into frame, and the physical layer transmits the data, and finally the reverse process happens at the destination and the packet element. So if you look at the structure of internet, is nothing but a network of networks, roughly hierarchical. At the center we have different tier 1 ISPs, for example the Verizon, AT&T, cable, wireless, national and international coverage provided by the ISPs. So this tier 1 ISPs is an ISP that has access to entire network region solely via its free and reciprocal peering agreement. An ISP is entirely controlled by a particular company like a Verizon or AT&T or Cable and Wireless. An ISP is an entity that provides or usually sells uh, access to the global internet. A tier 2 network is an internet service provider which engages in practice of peering with other networks, but which also purchased IP transit to each some portion of the internet. So if your packet passes through so many networks, right from tier 1 to tier 2 and tier 3 and the local ISP, so it's nothing but a network of networks. So so far we have looked at a wired networking structure. The wireless networking structure is also important depending on the architecture, data, and the applications we are talking about. We need to use the right wireless interface. If you look at the various evolution of world, wireless world started with 0G, or which became available after World War II. In those days, mobile operations set up the calls where there is only a handful of channel available. This mobile does not support handover feature, that is change of channel frequency. 0G refers to a pre-cellular mobile telephony technology in 1970s, such as uh, radio telephone, and some of the had cars before the advent of cell phones. Mobile radios telephonic system reduce modern telephones, so it has purely uh, kind of walkie-talkie kind of architecture in the so that's why it was not. Then we have the 1G, where first generation wireless telephony, where we have cell phones. They were analog phones and they were introduced in 1980s. In 1979, the first cellular system of world became operational by Nippon Telephone and Telegraph NTT Docomo in Tokyo, Japan. In Europe, two most popular analog were Nordic Mobile Telephone and NT. After the introduction of all these are offered handover and roaming capability, but the cellular network were unable to interoperate between countries. This was the main drawback of first generation of mobile networks. 1G has low capacity, unreliable handoff, poor voice links, no security since voice calls were played back in radio towers, making these calls susceptible to unwanted uh, issues. Then we have 2G, where we have a second generation of wireless phones based on digital technologies in the early 1990s. In 1991, 2G was launched in Finland. 2G provides services such as text message. That was a killer application which provides SMS, short message services, picture messages. 2G has security in both sender and receiver. All the text messages were digitally encrypted, which allows for the transfer of data in such a way that only intended receiver can receive. In 2G system uses digital mobile access technology such as TDMA and CDMA. TDMA was divides small signal in its time slots, while CDMA allocates each user a special code for communication or a multiplexed physical channel. Different CDMA technologies are GSM, IDN, IS. This was first 2G system. CDMA technology is IS-95, GSM, a group special mobile has origin from Europe. GSM is the most admitted standard for all the international roaming, while very common between mobile phone operators, enabling subscriber to use uh, their phones in any parts of the world. GSM uses TDMA to multiplex to 8 calls per channel in 900 and 1800 MHz bands. GSM can only deliver voice but also circuit switch data at up to 14.4 kilobits per second. Then we have 3G. 3G is a third generation mobile standard technology superseding 2G. The killer application was mostly data oriented. Wideband CDMA and heterogeneous voice and data networks were also incorporated. Uh, it was this plan was called International Mobile of IMT 2000 standard. 3G evolution of CDMA system led to a CDMA 2000. Several variants of CDMA 2000 were based on IS-95 and IS-95B technologies. 3G evolution was for GSM is IS-136 and PDC system led development of wideband CDMA, also called Universal Mobile Telecommunication Networks or UMTS. So here we have various nodes and radio network channel. So the UMTS, we have the core network and the UTRAN, Universal Radio Networks. Then we have 4G. 4G systems mostly provides interoperability between different parts of the networks. Killer application was Facebook, which falls high data rate 0 to 100 megabits per second in either server or the dataset is moved. Either server or dataset is moved at 60 km per hour, still it communication can be achieved. If the server and network stationary, then data rate transfer would be minimum of 1 gigabit per second. 4G is uh, 4G is the next generation of wireless networks that will replace 3G. So 5G is a fifth generation of networks where we are going to replace 4G with 5G. It provides multiple radio access technologies, and 5G uses OFDM network technologies, and is also IEEE 802.11a standard. Seamless session handoffs are possible, and the numbers may drive the bandwidth requirements 3GPP constraint. So the much faster than data rate we are talking about here is of the order of gigabits per second. Latency of the wireless is of the order of millisecond, and the dynamic spectrum multiple radio access is possible. One of the things I wanted to clarify is that there is a subtle difference between the Internet of Things and connected things. Connected things is when things are connected to each other, but they may not be connected to the internet. Internet of Things has been things that also are connected to the internet. So connected things are just interconnection of various components that they may not be connected to the internet, but internet things are connected things, but they are also connected to the internet. when you talk about Internet of Things networks, the most important uh, component is that the constraint in the communicating devices. Now let us look at why do we need different protocols for IoT, or why do we need different protocols for Internet of Things. First and foremost is that we are operating on energy constrained devices. That means battery operated devices. So battery's source is very limited, and it has a limited computational power, limited bandwidth for communication. So altogether we need different communication protocols considering the limited resources that is available. So this is a one of the slides. What we why do we need different protocols? We are working on a constraint node, constraint in sense of in terms of maximum node complexity. That means we have a limited flash or limited uh, memory, and also there is a constraint on the random access memory. All these constraints, we need to invent new protocols for communication and computation. Also we are talking about the constraint in the network. Low bit rate, there may be packet loss because we are working on low bandwidth, high variability in the bandwidth. So packet loss may be different, and the uplink and downlink path may be different as in a wireless medium. So the link characteristics could be different. The penalties for large packet will be more prone to errors. So there are various constraints in network communication as well. So let us look at the most important part, that is a battery constraint. In order to understand the basic concept, let us consider a Bluetooth low energy device that has a battery of 200 milliampere hours. So the unit of battery here is ampere hour. So the battery that we are assuming has, or the Bluetooth device has a battery capacity of 250 milliampere hour. So it can supply 250 million milliamperes of current for about 1 hour. Um, let's assume that this battery has a 3-volt battery. Therefore, the the power, which is nothing but the voltage into current into voltage into current, which is or let us consider the total energy of this this battery, that is 3 volt into 250 milliampere into 360 into 360 3600, which is around 2.7 kilojoules of energy. Hour has to be converted into seconds, that is 60 into 60 will give you 3600. So uh, this battery can uh, has an energy capacity of 2.7 kilojoules. Now assume that Bluetooth transmits like every 4 millisecond, or it transmits a packet of data in every millisecond, uh, sorry, every second. So that means what would be the life of this Bluetooth device if we have if we transmit every uh, 1 second. So for that we need to do some calculations. The device has a leakage of around 1 microamperes of current. So a leakage in the sense is standby current. So if you don't use this device, it would take approximately uh, 1 microamperes of current. So that means if you don't use the device at all, it will have it can supply uh, 1 microamperes of current about to 250,000 hours. That is 250 milliampere hour divided by uh, 1 micro, which is around 250k. So which is, if you convert into years, it is 28.5 years. Now in this particular example, where we are assuming that the device transmits every second one packet of data. Let's say each packet has let's say 128 bytes. So the device is transmitting at 1 megabits per second. So therefore, if you consider to 125 bytes at 1 megabit per second, which is around, it will take around for 1 millisecond. So when the device transmits, it takes 4 milliamps of current. When it is receiving, it like 3.3 milliamperes of current. So that is very important note. When it transmits, it takes more amount of current. When it receives slightly less, 3.3 milliamperes of current, and when it is in standby mode, it takes only 1 microamperes current. So as it's shown in this figure, uh, so every 1 second we transmit a small packet of data, which is around 125 bytes, and transmission takes around 4 milliamperes of current. So approximately 128 bytes takes around 1 millisecond to transmit, assuming that it is 1 megabits per second. So 1 megabits per second, 1 millisecond transmits around 1000. 1 millisecond transmit around 1000 bits. 1000 bits is approximately 125 bytes. So given that calculation, so we need to ramp up the current to this 4 milliamperes level, so that there should be some energy spent, which is roughly around which is roughly around uh, 5 microamperes of current. So 4 amperes of current, 4 milliamperes of current for about 1 millisecond, and 5 microamperes for the ramping up and ramping down. So this area occupied by this triangle, and the area occupied by this rectangle is around 4 milliamperes into multiplied by 1 millisecond. So the total current taken will be 4 microamperes plus 5 microamperes plus 1 microampere. So every second we consume around 10 microamperes of current. So assuming that every 10 microamperes of current taken by this device for transmitting one packet, or which is 128 bytes, we can have up to so 250 microampere hour divided by 10 micro 10 10 micro will give you around 25,000 hours. So the device will operate around 25,000 hours, which is equivalent to 25,000 divided by 60 into 60 or 365 will give you 2 years and 10 months of time. So this Bluetooth device will operate approximately. So here it is a calculation. The battery has a 250 milliamperes of amp hours, and ramp up down is around 1 milliamperes for around 5 millisecond. So that will give you around 5 microamperes. So average is 4 plus 5 plus 1, that is 10 microamperes. So total current is 10 microamperes. So 250 divided by 10 micro will give you 25,000 hours, which is divided by 365 will give you 2 years and 10 months of operation. So depending upon how much energy